the rate of a reaction is, well, some rate constant times the product of the concentration of the reactants. So the way we kind of would write a chemical reaction using chemical notation is this kind of notation here says that three molecules called A, B, and C react together and react with some characteristic rate constant K1, and that will form some product on the right hand side there. We call those A, B, and C the reactants. And the law of mass action then says that the rate of this reaction will be that rate constant K1 times the product of the concentrations of the reactants. We use lower cases to refer to the concentrations, uppercase to refer to the actual molecules. So the rate will be K1 times A times B times C. And from this then, we can then directly write down the differential equation model. So dA by dt, well, it's actually going to look the same for all of the three of them. A is being used up in this reaction, so we lose A when we do this reaction, and the rate is at K1 and ABC. So dA by dt is minus K1A, B, and C. So K1 minus K1A, B, and C. And actually, based on this reaction above, that will be the same equation also for B at E and C at E. So, as I say, the key thing about the law of mass action is that we can use it then to write down a differential equation model. Okay, so we did a few examples already in at the end of Thursday's lecture, and I kind of gave a final example, which I said to have a think about over the weekend, and try and think, when you kind of start extending this idea, how you could kind of write down the following reaction. So, just kind of reading this chemical reaction up here. 2 molecules of A combined with 1 molecule of B, and this double arrows indicates that this is a reversible reaction, so there's a forward reaction as we go from 2A plus B to the right hand side, and there's the backward reaction where we go from the right hand side to the left hand side. The 2 molecules of A combined with 1 molecule of B, and that forms A, B, and 2C. And the backward reaction, of course, goes in the other way. Okay, so how could we write down a differential equation model here? Some of you may have kind of had a go at that. So I'll give you kind of a few moments to have a think about this. I'm not sure if I can. Has everybody copied that down, that top part there? Okay, so there's 3 possibilities. Give you a couple of moments to think about this before we actually kind of go through it. I don't want. Let's give another possibility as D none. Don't spend too much time thinking about it. I mean, we will go through this in a moment. Just have a think through. Let's not come up with one of those A, B, and C, D. I'll give you another sort of 30 seconds or so, and then we'll take a kind of a poll on which one we think it could be. Okay, let's so as I've had a chance to think, I hope you've all kind of come up with an A, B, C or D. Let's now kind of go to the C. Okay, let's kind of take a poll on this. Okay, so if you kind of take your phones out, go to this website, www.menti.com, and enter this code, you should get up to this page here. And we see where people are kind of converting.
ادخل الويب سايت عشان اسجل. اكتب في الويب سايت. لا ادخل الويب سايت. حصل عليها نسبة. ذا يدور لنا السمعة شهوة ذكي منت بس
Okay, well that's probably enough responses. Don't worry. But a lot of people seem to be suggesting B actually. A few answers elsewhere. Let's now kind of go through this and then actually see if that's actually the right answer. So how do we kind of do this sort of problem here? Well, say it's a little bit more complicated than the previous one, but you can just break it down. What's the forward reaction here? Well, forward reaction, we have two molecules of A combined with one molecule of B. So we could write that as 2A plus B. So goes to something on the right-hand side with rate constant K1. And of course, this is just a kind of shorthand notation for saying A plus A combined with B form something on the right-hand side with rate constant K1. So the law of mass action says that the rate of the reaction is going to be the rate constant, which is in this case K1, times the product of the concentrations of the reactants. So we'll have K1 times the concentration of A, times the concentration of A, times the concentration of B. So the rate is going to be K1 A squared times B. So we get the rate of the reaction from the forward reaction is going to be of this rate here. We've got two molecules of A, so effectively we kind of have to introduce that A squared to kind of account for that. What about the backward reaction? What do we have here? Well, in this backward reaction, we have A plus B, and then plus two molecules of C. Okay, I can write that as 2C, but it's just kind of really spelling it out. That's A plus B plus C plus C. With rate constant K minus 1 goes to this, something that we don't really care about when it comes to writing down the rate. What is the rate in this case going to be? Well, it's going to be the rate constant K minus 1 times the concentration of A times the concentration of B, and then times the concentration of C times the concentration of C. So K minus 1, A, B, C squared. Okay, so when you've got a kind of a reaction where there's more than one copy of a particular reactant, that's going to affect the rate of reaction by introducing some power. So if it's 3A plus B, it will be A cubed times B. In this case, it's 2A plus B, so it's going to be A squared times B. Okay, so that's kind of written down our reactions. Now let's kind of think about what this means in terms of the differential equations. Okay, so when we now kind of convert this into our differential equation model, we're just going to have to think systematically through here on what's happening to our kind of molecules as we're kind of going through this reaction. This forward reaction, we start with 2 molecules of A and 1 molecule of B. The forward reaction goes at rate K1A squared B. But as a result of this reaction, on the right-hand side, well, we lose one of the molecules of A, but we still get a molecule of A. So you have to think about the net change. The net change in this forward reaction is we go from 2 molecules of A to 1 molecule of A. We lose 1 molecule of A. The reaction is at this rate K1A squared B. So we'll have dA by dt. We'll have one term, which is minus K1A squared B. Okay. So, now let's kind of think about the other part. Let's think about this backward reaction. Well, in this backward reaction, we start with 1 molecule of A, but as we kind of go from right to left, we gain a molecule of A, so the net change of A is plus 1. The backward reaction is at rate K minus 1 ABC squared, so we'll have a plus K minus 1 ABC squared. Okay, so that's kind of the dynamic state. What about B? Okay, well, B's going to turn out to be very easy when we start thinking about the net change. On the left-hand side, we have a molecule of B, and then as we go to the right-hand side, we still have a molecule of B. So the net change of B in the forward reaction is 0. So as a result of this process, there's no change in the number of molecules of B. And similarly, in the backward reaction, we start with a molecule of B on the right-hand side, and we still have a molecule of B after that reaction has taken place. So the net change of B for both forward and backward reactions is 0, and hence dB by dt is just going to be equal to 0. Okay, so that was actually very straightforward for B. The net change of B as a result of this reaction is 0, either way that you go, so hence we're never going to expect any change to the concentration. What about C? Just applying the same sort of logic. On the left-hand side, we don't have any molecules of C, but as a result of this forward reaction, we create 2 molecules of C. So for every time that forward reaction takes place, you create 2 molecules of C. And that's critical for then writing down the rate equations. The rate of the forward reaction is K1A squared B, but because we have a net change of plus 2 molecules of C, that's going to give me a plus 2 K1A squared B. We have to account for that fact that we've got a net change of plus 2 by adding an appropriate, by adding that kind of 2 in front of my rate of reaction. And similarly, in the backward reaction, we go from having 2 molecules of C to 0 molecules of C. We lose 2 molecules of C. So that's going to be minus 2 rate of the backward reaction, K minus 1 ABC squared. Okay. So actually, as people were generally sort of identifying, actually that case B was actually the correct one there, actually. So, and that's pretty well kind of the most complicated type of reaction that you're going to need to consider when it comes to using this law of mass action. We're going to do more examples on kind of applying this in the kind of the coming sections, because as I say, it's our kind of building block for writing down differential equation models. So get some more practice in doing this. Okay, so let's kind of now move on to the next section. And the next section, 2.3, is going to be looking at enzymes. So enzymes are biological catalysts.
كلهم بعض كلهم بعض.
They Okay, so as I say, an enzyme, the kind of point of an enzyme is that our kind of body is often wanting to kind of create lots of different things at different sort of times. For example, we want to create hormones at certain times and stuff like that. The way this kind of thing usually happens is that you kind of start with some sort of raw, basic substance, and that is transformed into the final form which the body can use. And the point of the enzyme is there to really kind of act as a way of speeding up that reaction, so it can happen very quickly when the body kind of needs it. And actually, you'll see, you'll see the results of enzyme reactions all the time, actually, because for example, if you cut an apple, then as you'll know, over time, it'll kind of go from a. Click play on this. Yeah. Over time, if you kind of cut an apple, the exposed face will slowly turn brown, and that's because of enzymatic reactions that are taking place. The actual kind of the enzymes are polyphenol oxidases, and it's the action of those when they kind of combine with the oxygen that hasten this browning sort of process. Okay, so that's an example of an enzyme reaction that you would kind of see, be very, very familiar with. But of course, they are absolutely fundamental in going on in our body all the time. And this section, as I say, is going to be kind of modelling some very basic enzyme reactions. You're going to need to introduce a little bit of terminology. So the first one is the raw material of an enzyme catalyzed reaction is called the substrate, and the end result is the product. So whenever I'm kind of talking about substrates, that's kind of just meaning the kind of the starting point of some enzyme reaction. Now I'm talking about the product, it's what I'm trying to create. Okay, so that's kind of basic sort of terminology. Well, the way, as I said, the idea of an enzyme sort of reaction is that your body's trying to change some substrate into some product. The enzyme is the body's way of speeding that process up. And that's important because then if the body regulates how much enzyme there is, it can control how quickly you want to do that process. So potentially you could generate a lot of something very quickly by modulating the amount of enzyme. Now the key thing is that enzymes don't actually kind of get used up as a result of this sort of reaction. They just speed things up. So at the end of some enzyme reaction, you'll have the same amount of enzyme that you started with. So what's the most simple model? So, simplest model is as follows. Enzyme combines with substrate form complex. Complex releases enzyme and product. So, as I say, kind of the simplest kind of model for how the most basic sort of mechanism of an enzyme basically involves sort of two steps. One where the initial step where the enzyme links together with the substrate, and that forms some sort of intermediate that we call the complex. And then this complex then kind of effectively releases the enzyme and generates the product in the process. And the way we could write this down is as follows. So in that kind of first step, the enzyme combines together with the substrate. That reaction results in some complex C. But actually, in that kind of first sort of step, this can take place in sort of two directions. So this kind of complex C is actually, rather than a kind of forward reaction, is actually a backward reaction. So, the first step just simply means that we have enzyme combining with substrate to form a complex. And then this second step says that the complex releases the enzyme as a product. And that one is just really a one-way reaction. It's very hard to go back in the other direction. It is sometimes possible, but it actually occurs at a very, very kind of small rate. So we have complex releasing the enzyme and forming the product. And actually, you can write that as kind of two reactions like this, but kind of the way you kind of actually see this usually presented is all as kind of one long string. So there's kind of two kind of separate processes can be kind of more compactly written just in this sort of form here. Okay, so as I say, we've got enzyme and substrate together form a complex. That's a reversible reaction. Complex then releases the enzyme and the product. So that's kind of my enzyme reaction. Let's now kind of write down the rate equations to describe this. Well, just an application of law of mass action. So, well, let's kind of still break it down to term by term. We've got a forward reaction where E plus S goes to form C at rate K plus 1, rate K1. The law of mass action say that the rate of that is going to be K1 times the concentration of E times the concentration of S. We've got the backward reaction where C with the rate K minus 1 forms E plus S. We've only got one reactant, which is the complex C, so the rate of this one is going to be K minus 1 times the concentration of C. We've also got then this third reaction here where C forms enzyme and product. That's with rate constant K2. And again, the only reactant is the complex here, so the rate of that one is going to be K2 times C. Okay, so law of mass action, just to say, kind of allows me to kind of write down the rates of the reactions for effectively the three reactions that we've got going on here. We've got a forward and a backward reaction in that first step, and just a forward reaction in the second. Once you've got that, it's then kind of quite straightforward to write down your kind of differential equation model. Let's start with my substrate. So dS by dt. We just kind of have to go through these various reactions and see where things are being kind of created or used up. In this first reaction, we use up a molecule of S. E combines with S to form C. The rate of that reaction is K1 ES. So we're going to have a minus K1 E times S. We create a molecule of S in this kind of in the backward reaction of the first step. So create a molecule S here. The rate is K minus 1C. So we'll have plus K minus 1 times C. And that's it for my S, because it just S is only appearing either as a reactant or a product in these first two processes. What about C? Well, C is being created in the first step at rate K1 ES, so we'll have a plus K1 ES. He's been oh, sorry, C is being created in the first step. C is being used up in this step with rate K minus C. We'll have a minus K minus 1C. C is also being used up in this reaction here. So we'll have a minus K2C. Okay, so what about E? Well, E is being used up in the first reaction, so we use a molecule of E. So we'll have a minus K1ES. E is being created in this one and in this one, so we're going to have a plus K minus 1C plus K2C. Okay, so that's my kind of equation 3. Finally, for P, P by dt, well, there's only one place where P is appearing. It's appearing as the product in this third reaction. The rate of that reaction is K2 times C, so we just have a plus K2C there for my P. As I say, that the law of mass action is safe to spade. Useful way to be able to write down these rate equations. That's kind of the differential equation model. And actually, in the next section, we're going to do quite a sort of a sophisticated analysis to understand the dynamics of this sort of system. So that's going to be the next section. But for this section, I'm just going to kind of note a couple of properties of this. So one is we have a conservation law. What do I mean by conservation law? Well, effectively, if we kind of combine together these equations, or some sort of set of these equations, we can basically get the terms to cancel. And in fact, if you look at the equation for C and the equation for C, basically they're just kind of reversed by the signs. So if we kind of add dc by dt and dE by dt, we'll have dc by dt plus dE by dt is equal to 0. Those terms on the right hand side match, and that actually implies something very, very important. If dc by dt plus dE by dt is 0, then by integrating C of t plus E of t is going to be some constant for all time. In other words, the amount of enzyme plus complex is a conserved is conserved over the full reaction. And that makes sense for this reaction because basically what's happening here, I said earlier, enzyme is never used up. So in this reaction, we start with enzyme and substrate. It is linked together with the substrate to form the complex, but it's still there. It's kind of in this complex, which is the enzyme added together with the substrate. And then the complex releases the enzyme and creates the product in the process. So C of t plus E of t is a constant. And that's going to be very important for the analysis that we're going to be able to do, because at the moment we've formulated a fourth order differential equation system, but through this property we can effectively eliminate either my C or my E, because C is defined in terms of E. So that's going to be very important for reducing the order of the differential equations. And another thing that is going to be very important is actually, when it comes to studying the dynamics of the system, we can actually completely ignore this equation for P. P has kind of got an equation down here. It depends on C. So understanding the dynamics of P is, of course, you need to know what C is doing, but P is not appearing in the right-hand sides of the first three equations. So if we were kind of trying to study the dynamics of S, C and D, we don't need to care at all about what P is doing. And an example of that, write that down again. So one is we have a conservation law, and the P is decoupled from the other equations. We don't need to know what's happening with P to understand the behaviours of S, E and C. And those are going to be looking for kind of conservation laws and looking for parts of the equations that are decoupled is absolutely fundamental when trying to analyse these equations. Because typically when you're dealing with biochemical reactions, you typically generate quite high order differential equation systems. This is a very simple model. We just generated four differential equations. But already that would be very difficult to analyse. You know, like a kind of stability analysis in the last chapter was kind of dealing with second order systems. Identification of conservation laws and parts that decouple is essential for reducing the order. Okay, so anyway, we're going to come back to the importance of that in the next sort of section. Okay, so that's my kind of basic enzyme reaction. Let's do a kind of a second example. And then I'll kind of give a quick sort of exercise on this as well, actually. So.
لكن عرفنا احنا نبدل إليه خلاص. خليك هذا ولا شيء.
As I said, that kind of first model for an enzyme reaction was about the simplest possible one that we could come up to. It's really distilling the kind of the behaviours of enzymes down into the kind of the simplest possible consideration. But a lot of the times things are a little bit more complicated. And the next second example is what is called a cooperative behaviour. And in cooperative reactions, the substrate may bind to several points on an enzyme. Okay, so what I kind of mean by this? Well, as I say, kind of what enzymes do effectively is they link together with the substrate, and then once linked together, they can kind of change the properties of that substrate to create the product, and then release the enzyme in the process. So the way to kind of think a little about these enzymes is, you know, or these kind of chemical reactions, a bit like kind of jigsaw sort of pieces. If you've got some sort of enzyme, then you know it could kind of represent some kind of piece like this. So that's kind of my enzyme, and then my complex could have a kind of a, you know, kind of be a corresponding piece like this. And because they kind of have a part that kind of is able to couple together, that kind of allows the enzyme, and sorry, that should be substrate here. That kind of allows the enzyme and the substrate to join together to form this kind of complex. So, in a second, these kind of properties of these kind of biochemical molecules is that by their kind of configuration, they can effectively, their reaction kind of involves kind of joining together in a certain way. So in a complex sort of, a cooperative sort of reaction, the enzyme, rather than having one binding site, can actually have two. So rather than kind of that kind of piece like this, you know, it could kind of have kind of 2 points. And that would kind of allow the enzyme to join the substrate in 2 different ways. So E plus substrate would kind of allow you to kind of link together to form a complex like this, or a complex one. But then of course the enzyme still has a kind of a free binding point, so you could also have then a case where that kind of complex one adds another substrate, and that kind of forms kind of another complex. Call it complex 2. So the enzyme, as I say, has this kind of extra binding sites, and indeed, actually, it's not even necessarily 2. It could even be 3, 4, 5 sort of points where the enzyme is able to kind of bind, and therefore potentially it can that enzyme can act to convert lots of molecules of substrate at the same time. So in a cooperative reaction, we have kind of this sort of phenomena here, and the kind of a basic model for this. It's already going to look a lot more kind of complicated than the one that we were dealing with earlier. Is that E plus S forms K1, K minus 1 complex C1. Okay, that's kind of my step one here. Enzyme plus substrate forms this first complex up at this point there, and potentially from that complex 1, that could already convert, that enzyme could just simply release that substrate, converting it into product in the process. So that kind of C1 could then release the enzyme and form the product with rate K2. Okay, so that's that part of it is exactly the same as the kind of previous reaction. Enzyme and substrate form a complex, and then that kind of releases the enzyme and creates the product in the process. But of course, we now have to count that there's potentially this second sort of step where this kind of complex, which has got this kind of extra binding site, could also add another molecule of substrate. So, effectively, that second one says that E plus C1 goes to form the second complex C2. For this one, A3, A minus 3. And then that complex C2 can kind of release can kind of work to kind of release one of these substrates, converting it into product. And so product plus that complex 1. Because then say from this form here, if it kind of just if it converts this piece of substrate into the product, that bit will disappear and you'll be back to the complex 1 left.
It's not C1 plus X.
So it's C.
S plus 7. The second equation.
Oh, sorry, yes, absolutely. Thanks for that.
No,
So that should be C1 plus S, yeah. Yeah, thanks. Okay. Don't think there's anything else wrong with that. Yeah. Okay, so that's kind of an example of a cooperative sort of reaction. Okay. Now let's kind of write down the differential equation model for this. Well, it's going to become a lot more tedious now because we've got so many kind of reactions going through it. So you just kind of have to kind of grit your teeth and kind of go through the process. Look at the substrate. Substrate is lost in this very first reaction up here. So we're going to have a minus K1ES. Substrate is created in the backward reaction of that kind of first step. So we're going to have a plus K minus 1 C1. Substrate is also being lost in the forward step of this one here. So C1 plus S forming C2. So you're going to have a minus K3 S C1. But we gain that substrate if we go in this reversible way from C2 to S plus C1. So plus K minus 3 C2. And I think that's all the terms for S. dE by dt. Well, E, what do we have? E is kind of lost in that kind of forward step of the first reaction, so minus K1ES, but we gain it in the backward reaction of the first step, so plus K minus 1C, plus we gain it as the complex 1 forms enzyme of product, so plus K2 times C1. And that's it for E, because E's not appearing in that kind of second sequence there. C1 by dt. Well, C1's created in the first, as enzyme and substrate come together, so you're going to have plus K1ES. It's lost in the backwards reaction of rate to minus K minus 1C. It's lost as we kind of go from C1 to enzyme cross product, so minus K2 times C.
Isn't it a C1?
So yeah, should be a C1. Yeah. So we've got too many kind of subscripts here actually. So okay, so we're kind of losing. C1. Yep. We also kind of have C1 appearing completely in that kind of second sequence of equations. So C1 and S form C2. So we're going to have a minus K3 C1 times S. We gain it at a rate plus K minus 3 C2. And we gain it also, we put the K4 up here. We also gain it at a rate plus K4 C2. So 6 terms there for C1, I think that's all of there. I think we're nearly there now. C2 by dt. C2 is only kind of appearing in this kind of second sequence of reactions. So for that one, we're going to have a K3 C1S minus K minus 3 C2 and minus K4 C2. And finally, my equation for P, well, dP by dt. P is the product. It's only ever kind of created at the very kind of end step here. It's created in the kind of the C1 releases the enzyme and the product, so it's going to have a plus K2 C1, and it's also going to be kind of created in at the end of that kind of second sequence plus K4 C2. Okay. Well, again, as I say, it's there's a lot more kind of processes involved here, but it's still just this kind of same basic law of mass action that we're kind of using to kind of write down these equations. Okay. And similarly to the previous sort of case, this is kind of a fifth order differential equation to the system, but you can still find conservation laws. So see if you can have a look at these equations, see if you can kind of find some conservation law in this sort of case here. And we can also still note that the equation for P is still decoupled from the other ones. So P depends on C1 and C2, but none of the other equations depend on P. So it's possible to reduce the complexity of this model through those sort of considerations. Okay, so that's kind of an example. Well, just to kind of finish off here today, I'm not going to kind of do this, but I believe this is a kind of class exercise to think about between today and tomorrow. So, exercise. Write down the differential equation model for the following trimerization reaction.
كم نقول إذا فطرت قهوة هذه كلاسة.
Okay, so
كلاس قهوة شو الحالة الاسم
I kind of explain what I mean by this
شو اللي معي
in a
الاسم
moment. So this is kind of a
أتكلم معه.
reaction where two molecules of A two molecules of A combine
صدورها
together
بالكوليكشن
to form a molecule of B.
بالكوليكشن حقنا
2A goes to B with,
خلي تساعدني هي
that's going to be a reversible reaction, K1, K minus 1.
فهمت
And
علي؟
then in a second step,
خلط
A plus B
it's minus 1
forms C with rate constants K2 and K minus 2. This is an example of what's called trimerization. And basically in this kind of reaction, effectively the same molecule is steadily joining together. So this first step, effectively, it's kind of two molecules of A, and they kind of join together to call well, B is what we would call a dimer. So those two molecules of A kind of form a dimer. These are what we would call monomers. That's kind of my first reaction, where the two monomers combine together to form a dimer. And then in the second step, that kind of dimer joins with another molecule of A. So a monomer combines with the dimer, and that creates the trimer. Okay, so you've effectively got this process where molecules are steadily coming together and accumulate. So write down the differential equation for this reaction and then identify a conservation law. Okay, and as I say, I'll kind of leave that as an exercise or something to think about between today and tomorrow before we'd actually kind of then